Okay, so we're doing problems from chapter 8. So this problem says, what is the capacitance of a large Van de Graaff generator given that it stores 8 millicoulombs of charge at a voltage of 12 megavolts. Okay, so the capacitance is defined as how much charge you hold per unit volt. And this is 8 millicoulombs and 12 megavolts. And coulombs per volts are farads, and this is 10 to the minus 9, so 0.67 into 10 to the minus 9 farads, 0.67 nanofarads. Okay. Okay, this problem says if the capacitance per unit length of a cylindrical capacitor is 20 picofarads per meter, what is the ratio of the radii of the two cylinders? Oh, I guess I will have to. I don't remember the formula. So let's see. All right, there we go. So the length divided by that. Okay. So what is the ratio of the radii of the two cylinders? They want the ratio of the two radii of the two cylinders. So here is the. This is A, that is B, okay, and that's the ratio they want. Okay. So 2 KEC or log B by A equal to all right. So and B by A equal to e to the power L. Okay. Exponential they give us this value, okay, the capacitance per unit length. Capacitance per unit length is given to be that. Yeah. So let's plug in these values. Exponential 1 over 2 Ke, the Coulomb's constant is 9 times 10 to the 9, and this is 20 picofarads. Which is 10 to the minus 12 farads per meter, and I left out the units there. So this is 10 to the minus 3, 10 to the minus 2, that's 36, so exponential 1 over 0.36. So roughly e to the power 3, which would be roughly about 25. So let's see. Okay, so this is 16.1. Okay, so this radius is 16 times greater than that radius. Okay. Okay, this says an empty parallel plate capacitor has a capacitance of 20 microfarads. How much charge must leak off its plate before the voltage across them is reduced by 100 volts? Okay, so capacitance is that. Okay. And so you can think of this as, how much charge do you add and the voltage increase gives you the same capacitance. Okay, so this is the number of charge that must leak, the amount of charge that must leak off. So this charge leaks off and the voltage reduces by that much. Okay, so this is 20 microfarads, 100 volts. So this is 2 into 10 to the minus 3 coulombs. So 2 millicoulombs has to leak off for the voltage to drop by 100 volts. This says find the net capacitance of the combination of series and parallel capacitors. Okay. So what you want to do is reduce this to a single capacitance. Okay. And the two procedures is how to add parallel and series. Okay. So you do that wherever you see parallel combination, you'll reduce that to a single capacitor. Here's the series combination. You'll reduce that to a single capacitor. Okay. So parallel combination, you just add them together. So this would be 15 plus 0.75, 15.75. And series, so parallel combination, C is just C1 plus C2. And series combination, the equivalent capacitance is given by that. Okay. So these two, you're just adding them, that's 15.75. These two, okay, so let me add those two. 1 over C equal to 1 over 5 plus 1 over 3.5. And we'll keep everything in microfarads. If this is in microfarads, that will be in microfarads. So this is equal to 5 times 3.5, 8.5. .06 microfarads. Okay. So what we have is this circuit reduces to, so this is 2.06, that is 8, and they're all in microfarads. Okay, so this has reduced to this. This is simpler. Now we'll add these two guys in series, and then those three will be in parallel. Okay, so let's reduce this to a single capacitor. Okay. So these guys are in series, so you'll use this formula to find that. Okay, so for the series combination, it's 1 over C1 plus 1 over C2. Now you guys are experts at this, so I'll just, okay, so this is 15.75 times 1.5 divided by 15.75 plus 1.5. Well, here's one thing you want to remember about a series combination. Okay, so when you see this equation, you see this fella is this plus this. So this fellow has to be bigger than this and bigger than that. So this has to be smaller than either one of those. Okay, so when you do a series combination, the resultant is smaller than the smallest one. Okay. All right, so this reduces to and now this is parallel combination, so you just add them, 8, 10.06 plus 1.37, 11.43. Okay, so that's the single capacitance that mesh is equivalent to. Okay, this capacitor is equivalent to 11.43 microfarads. Okay. All right, so this whole thing acted like that, but the reason you had this was because you wanted to see different portions of the circuit, so different pieces of the voltage and so on. Okay, and that's why you had that kind of division in the circuit. Okay, each was doing something. So, for instance, the voltage across these two are the same. The voltage across this is, so on. You were dividing the voltage, so to speak. All right, so this next problem says a 2 microfarad capacitor and a 4 microfarad capacitor are connected in series across a 1 kilovolt potential. The charged capacitors are then disconnected from the source and connected to each other with the terminals of like signs together. Find the charge on each capacitor and voltage across each capacitor. Okay. Okay, so these were in series, and then what you did was you disconnected them and connected them together like that. Okay, so when you connect them in series, what is the same on these capacitors? So here's what happens. This is how you remember it. Okay, what happens when you connect capacitors? Electrons flow from here to there. So let's say 10 electrons flowed from here to there. You collect 10 electrons here. These 10 electrons will repel 10 electrons. Remember, capacitors, the opposite conductors always acquire the same charge. So this will repel 10 electrons there. 10 electrons will collect there, and these will repel 10 electrons. So when you connect capacitors in series, the charges are the same. Okay? And then when you disconnect them from here and reconnect them like this in parallel, what happens is charges redistribute such that now what is the same? So when you connect like this, the voltages are the same. Okay? So the voltages will be the same. And so let's say the charges now are Q1 and Q2. Okay? So so when you reconnect them, you see 2Q will be Q1 plus Q2. Okay, so before the charges redistribute, this is Q and this is Q, and the charges will redistribute such that Q1 and Q1 plus Q2 is Q2Q. Okay, and then what do we have? C1 is equal to Q1 over V equal to all right, so here are two equations and two unknowns. Q1 and Q2 are unknowns. Okay, so all we have to do is find the charge Q. Okay, and the way you find the charge Q is what you do is you reduce this to, by the way, this is 1,000 volts. So what you do is you reduce this to a single capacitor, find the charge on that capacitor, and that will be the charge on these two capacitors. Okay. So now let's find Q first. Okay. So let's, I'll take this guy. So this reduces to a series combination. C is C1, C2 over C1 plus C2. 2 times 4 divided by 2 plus 4. That's 8 over 6, which is 1.33 microfarad. So this is equivalent to okay, so Q is C times V So the charge on this is Q, and that's the same charge on this guy, each of these guys. Okay. So now that we have this charge, you have two equations and two unknowns, and we can solve this. Okay. All right, so let's do this. So this is millicoulomb, and Okay, so Q1 plus Q2 is, we can work in millicoulombs, 1.33, and Q1 over C1, Q2 over C2. So Q1 is C1 over C2 times Q2. Okay. So C1 is 2 microfarads, C2 is 4 microfarads. So Q1 is 1/2 Q2. Yeah. And we'll substitute this 1/2 Q2 plus Q2 equal to 1.33. And then Q1 is yeah. All right, I'm going to walk you guys through this thing again because there's a bit of algebra. All right, so here's what's going on in this problem. You connected 1,000 volts to these two guys in series. When you connect capacitors in series, the charges are the same. And then you disconnect these guys. So here are these two guys. Oops. This has a charge Q, this has a charge Q. You disconnected them, and then you connect the two. Okay. So what happens is some charge will flow from here to there, let's say. But the total charge on these plates is the same, remains constant. It was 2Q to begin with, so Q1 plus Q2 will be equal to 2Q. That's where you got that information from. All right, well, and how do the charges redistribute? The charges redistribute such that the voltages have to be the same. Okay, and this is the capacitance is charge over voltage, so voltage is charge divided by capacitance, and since the voltages are the same, Q1 by C1 should equal Q2 by C2. All right, so there are your two equations and two unknowns. The two unknowns are how much charge is on one and how much charge is on the other. Okay. Now, before you could solve that, you had to find out Q, the original charge. Okay. And the way you find this charge is, well, this is a series combination, replace it by a single capacitor, and the charge on that capacitor is the charge on these guys. Okay. It's like you can think of these two plates, and then you introduce two more plates in between. That's all. Okay. So to find this charge, what you did was you reduced this guy to a single capacitor, found the charge on that guy, and that is the same charge on these guys. Okay. And that charge was 1.33 millicoulombs. Okay. So now you know this guy, you know these guys, so Q1 and Q2 are the only unknowns, and you solve for that. Okay. All right. This problem says a capacitor has a charge of 2.5 microcoulombs. When connected to a 6-volt battery, how much energy is stored in the capacitor? Well, the energy stored is 1/2 CV squared. the energy stored is 45 millijoules. I mean microjoule. You guys remember how much energy is stored in the capacitor in a flash bulb circuit? It was in the notes. About 20 joules. So 1,000,000 times greater than this. Okay, this problem says, suppose you have a 9-volt battery, a 2 microfarad capacitor, and a 7.4 microfarad capacitor. Find the charge and energy stored in the capacitor if the capacitors are connected to the battery in series. Do the same in parallel combination. Okay, when you want, so what this problem illustrates is if you want to store energy and you have a bunch of capacitors, what you do is you connect the capacitors in parallel. Okay, so that's when you store the maximum energy. Okay. So parallel combination is good for storing energy. Okay, so 2 microfarads. Okay, what you have to do is you got to reduce this to a single capacitor. Okay, so this is and the value of that single capacitance, C, is 7.4 into 2 divided by 7.4 plus 2. That's how you do a series combination. Well, let me put down the formula. Okay, so that's the equivalent value, and the energy stored is 1/2 CV square, 1/2 C is 1.57 microfarads and 9 volts square. Okay, 64 microjoules. So in this series combination, that's how much energy you've stored. Let's do the same thing for parallel combination. Okay, so in a parallel combination, now the equivalent capacitance is just the sum of the two. And the energy stored is 1/2 9.4 into 10 minus 6 9 volts squared. Okay, so you can see that it's 380 microjoules versus 60 microjoules. So almost 6 times more the energy with the same capacitors. Okay. And if you look at your notes, the fusion reactors at Sandia National Lab and Lawrence Moore, so they store a whole bunch of energy in capacitor banks which are connected in parallel, and then those capacitors are fired through a laser which shoots at a pellet. Yeah. So when you want to store a lot of energy, you store in banks of capacitors that are connected in parallel. A parallel plate capacitor has a charge of magnitude 9 microcoulombs on each plate and capacitance of 3 microfarads when there is air between the plates. The plates are separated by 2 millimeters. With the charge on the plates kept constant, a dielectric with K equal to 5 is inserted between the plates, completely filling the volume between the plates. What is the potential difference between the plates of the capacitor before and after the dielectric has been inserted? Okay. So part A. So charge is 9 microcoulombs and a capacitance of C equal to 3 microfarads. Yeah. With air between. Okay, and the separation between the plates is 2 millimeters. With the charge in the plate kept constant, now what you do is you insert a dielectric. What is a dielectric?
Something that goes between the plates and changes how much energy it can take us from.
What are the electrical properties of the dielectric? Yeah, it's an insulator. That's okay. It has no free charges. So it's doing multiple things. Like Lee said, it increases the capacitance, it decreases the electric field, it provides insulation, prevents these plates from touching each other. So it provides mechanical support, it increases the capacitance, it lets you store more energy and all that stuff. Okay. Okay, so with the charge on the plate kept constant, a dielectric constant Ka is inserted between the plates, completely filling. What is the potential difference between the plates of the capacitor? Okay. Now, we'll call this C's naught. That's the capacitor with air. And now C is kappa C naught. So the capacitance increased by that, 5 times 3 microfarads, which is 15 microfarads. Yep. Now, the charge is the same, so the new potential is Q over C. Okay. They ask you, what is the potential difference between the plates after the dielectric has been inserted? So the charge is still the same, 9 microcoulombs, and the capacitance is 15 microfarads. Okay. So you see, the capacitance increased by a factor of 5 and the voltage decreased by a factor of 5. And the voltage, remember, the voltage was equal to E times D, the electric field. So the reason the voltage decreased was the electric field decreased. The strength of the electric field decreased. Okay, how did the electric field decrease? Okay, the plates had produced an electric field like that, and the dielectric, because of induced dipole moments, introduced a field in the opposite direction, and it decreased the effective fields. Okay? So that's what happened. All right. So the voltage is that, and that is equal to 9/15 is 3/5 0.6 volts. So the micro cancels and capacitance, coulombs divided by farads is volts. Okay. What is the electric field at the point midway between the plates before and after the dielectric is inserted? And we've said that when you insert the dielectric, it reduces the field, and we're going to show that to you now. Okay. So V naught was equal to Q over C naught. That was equal to E naught times D. Okay. So Q was 9 microcoulombs divided by 3 microfarads. So the field before the dielectric was inserted was equal to 3 divided by 2 millimeters, 2 into 10 to the minus 3 meters. Okay. That's 3 volts. So volt per meter. So it was 1500 volts per meter. So this was before the dielectric was inserted. And after the dielectric was inserted, E times D equal to Q over C. And we found Q over C. We found Q over C to be 0.6 volts. All right, so this was the value of the electric field before the dielectric was inserted, and this was the electric field after the dielectric was inserted. Do you see any relationship between them? It reduced by the factor of the dielectric constant. Yeah. All right, so again, a dielectric is an insulator. It does several jobs. First, one of the things it does is it provides mechanical support, prevents the plates from shorting each other. It increases the amount of energy you can store, okay, and so on. Okay, so here's a capacitor with 2 different dielectrics present in there. Okay. Show that the capacitance is given by this. Okay. So if you have a single capacitor, then single dielectric, then the capacitance is given by this. this is the capacitance without the dielectric, and you insert a dielectric, that's the factor. So when you guys insert this this dielectric, it seems like the effective dielectric constant is given by that. Okay. Now the question is, how do you prove that this is equal to that? Okay, so here's the trick. So if you think of this as one capacitor and this as the other capacitor, then how are these two guys connected? They are connected in parallel. Okay, so C, we'll call this C1, C2. The area A1 is A over 2, A2 is A over 2. Okay, so the equivalent capacitance is C1 plus C2. We've broken that up into two capacitors. The first capacitor is kappa 1 A1 over epsilon naught D plus kappa 2 epsilon naught A2 over D. A1 is A over 2. Okay, so you get kappa 1 over 2 epsilon naught A over D plus kappa 2 okay, so this is okay. So that's the new capacitance. And you see this is the effective dielectric constant. So this would be a little hard to prove, but in general you would think that if you fill this thing with dielectrics kappa 4, kappa 5, the effective dielectric constant would be the fractional volume. Okay, so fractional volume 1, kappa 1, and so it would be the weighted average fractional volume of kappa 2 and so on. Yeah. All right, that finishes the problem. So